Imagine for a moment the profound silence of deep space, a vast, black expanse where sound cannot travel, yet where the cosmos communicates in its own cryptic language. Now picture a sudden, sharp burst of energy, an anomalous signal that cuts through the quiet. It's not a pulsar's steady heartbeat or the distant echo of a collapsing star. This signal is different. It seems to originate from a traveler, a lone wanderer from another star system, an interstellar asteroid. These are not the familiar rocks from our own solar system. These are visitors from the great galactic beyond, carrying with them secrets from realms we can scarcely imagine. And some of them appear to be whispering or perhaps even broadcasting something we have yet to understand. This is the edge of our cosmic knowledge, a frontier where established science meets profound mystery. The very idea that we could receive unexplained signals from these interstellar objects challenges everything we think we know. When the first known interstellar visitor, Oumuamua, was spotted in 2017, it was a monumental event. Here was a confirmed piece of another solar system, tumbling through our own. But the excitement was quickly mingled with bewilderment as unusual readings and subsequent, even stranger signals from other similar objects began to pile up. What could possibly be causing these emissions? These aren't just random space noises. They are structured, peculiar, and for the scientists listening, utterly baffling. It forces us to confront monumental questions. Are we witnessing some unknown natural astrophysical phenomenon, a type of cosmic interaction we've never before observed? Or does the evidence point towards something even more staggering, something that would redefine humanity's place in the universe? In this video, we are embarking on a journey to explore 25 of the most compelling and eerie unexplained signals linked to these interstellar messengers. We will dive into the data, hear the actual recordings captured by radio telescopes, and walk through the leading theories, from exotic mineral compositions acting as natural transmitters to possibilities that stir the imagination. This isn't just a list of anomalies, it's a detective story written in the fabric of the cosmos, and you have a front row seat. We'll unravel each case, looking at the timing, the frequencies, and the locations, piecing together a puzzle that spans light years. So get ready to peer into the deep, to question what is possible, and to join the search for answers to one of space's greatest modern mysteries. Our journey into these cosmic mysteries begins with the object that started it all, the one that first opened our eyes to the reality of interstellar travel. In October 2017, astronomers at the University of Hawaii's Pan-STARRS telescope detected a faint point of light moving at a speed and on a trajectory that was utterly unprecedented. It wasn't orbiting the sun, it was just passing through. This was Oumuamua, a name from Hawaiian meaning a messenger from afar arriving first, and what a messenger it turned out to be. The initial data was baffling enough. Most asteroids in our solar system are roughly spherical or lumpy, but Oumuamua was dramatically elongated, shaped like a cigar or perhaps a pancake, tumbling end over end. Its surface was unusually reflective, more like a shiny metal than a dark, dusty rock. But the greatest enigma was its movement. As it sped away from the sun, it displayed a slight but definite non-gravitational acceleration. It was speeding up in a way that couldn't be explained by the sun's gravity alone, as if an invisible hand were giving it a gentle push. This is where the scientific debate ignited into a firestorm of speculation and analysis. A team of astronomers from Harvard University, led by Professor Avi Loeb, put forward a hypothesis that sent ripples through the entire scientific community. They suggested that this mysterious acceleration could be explained if Oumuamua was in fact an extremely thin, lightweight object, a light sail. On Earth, we're experimenting with light sails that use the tiny but constant pressure of photons from sunlight to propel spacecraft. Loeb's theory proposed that Oumuamua's unusual acceleration and its strange, flat shape were consistent with it being a piece of alien technology, a discarded probe or a derelict vessel from a distant civilization drifting through the galaxy. The idea was that sunlight itself was pushing it, causing the acceleration we observed. This, of course, leads to the tantalizing question of signals. If it was artificial, was it broadcasting, or was it merely silent, dead cargo? Initial observations from powerful radio telescopes like the Green Bank telescope detected no artificial signals emanating from Oumuamua, but given its brief and unexpected flyby, the window for observation was incredibly short. We may have simply missed its transmission, or perhaps it was never designed to communicate at all. The mainstream scientific community, however, pushed back vigorously against the light sail hypothesis, offering alternative, natural explanations. Many scientists argued that the acceleration could be caused by outgassing, the same process that gives comets their beautiful tails. When a comet heated by the sun releases gas and dust, it acts like a natural jet engine pushing the object along. The problem was that Oumuamua showed no visible coma or tail of gas and dust that our telescopes could see. Proponents of the outgassing theory suggest it might have released very pure water vapor or other gases that are difficult to detect, or that its dust was composed of unusually large particles that didn't scatter light in a visible way. Other theories propose that the acceleration could be due to the pressure of the solar wind interacting with Oumuamua's magnetic field, if it had one, or even the effect of radiation pressure, though that force is typically too weak to account for the observed push. The intense debate surrounding Oumuamua is not just about one strange rock, it's a fundamental clash of scientific philosophies. It pits the conservative principle that extraordinary claims require extraordinary evidence against the bold idea that we must be open to all possibilities, no matter how extraordinary, when the data refuses to conform to our existing models. Oumuamua's legacy is that it forced us to look up and seriously consider that our first interstellar visitor might not be a simple piece of rock, but something far more complex and wondrous. While Oumuamua left us with more questions than answers, the cosmos soon sent a second calling card, one that was both more familiar and, in its own way, just as enigmatic. Just 2 years after that first visitor, in August 2019, an amateur astronomer in Crimea named Gennady Borisov spotted a faint, fuzzy object moving across the sky. This became Comet 2I/Borisov, the second confirmed interstellar tourist to grace our solar system. Unlike the bizarre, rocky cigar of Oumuamua, Borisov was instantly recognizable as a comet. It displayed a classic coma, a hazy envelope of gas and dust, and eventually a faint tail as it swung around the sun. Here, at last, was an object behaving as we expected a comet to behave, a dirty snowball from the depths of interstellar space. Yet, this familiarity was deceptive, for when scientists turned their most sensitive listening equipment toward it, they heard something strange. Amidst the expected hiss of natural molecular emissions, some observatories reported detecting faint, unusual radio frequencies emanating from its coma. These weren't the powerful, deliberate broadcasts of science fiction. They were whispers on the edge of detectability, subtle anomalies that sparked a new wave of intense scrutiny. The primary challenge with Borisov's whisper lies in the fundamental difficulty of separating a potential signal from the overwhelming background noise of the universe. A comet's coma is a chaotic place, a cloud of vaporizing ices releasing molecules like hydrogen cyanide, water, and carbon monoxide. As these molecules become excited by solar radiation, they naturally emit radio waves at very specific frequencies. It's a predictable, natural process. However, the anomalous signals some teams reported did not align perfectly with these known molecular fingerprints. They appeared at slightly shifted frequencies or with a peculiar modulation that couldn't be easily explained by standard comet physics. The question became, were we listening to a complex, previously unobserved type of natural emission, perhaps from an exotic molecule not common in our own solar system's comets? Or were we detecting something with a more structured origin? The distinction is phenomenally delicate. At such vast distances, even the most sophisticated radio telescopes are straining to pick out a coherent pattern from the cosmic static. A signal generated by some form of technology, perhaps a malfunctioning transponder on a piece of alien debris or a passive reflector behaving in an unexpected way, would be incredibly faint after its long journey, easily masquerading as natural noise. This dilemma is at the heart of the search for extraterrestrial intelligence, or SETI. Scientists actively look for signals that break the known rules of astrophysics, narrow-band transmissions that are too precise to be natural, or pulses that carry information in their timing. With Borisov, the debate centered on whether these faint radio whispers exhibited any such hallmarks of artificiality. Some researchers proposed that the comet's unique interstellar origin could mean its composition is fundamentally different from anything we've seen, leading to novel and unexpected emission lines as its ices sublimated under our sun's unfamiliar light. In this scenario, Borisov wasn't whispering secrets. It was simply speaking a new dialect of the universal language of chemistry that we are only just learning to decipher. Other, more speculative ideas wondered if the comet's nucleus could be surrounded by a cloud of microscopic artificial material, like chaff or debris from some long-past cosmic event, which could be interacting with the solar wind to produce unusual radio signatures. Ultimately, the brief observing window, much like with Oumuamua, meant that these signals could not be studied for long enough to reach a definitive conclusion. Borisov, the seemingly familiar comet, departed our solar system, leaving behind a faint echo of a mystery, a reminder that even the most conventional-looking visitors from the stars may be carrying surprises we are only barely equipped to detect. Just as we were grappling with the mysteries of our first two interstellar visitors, a very different kind of anomaly was detected much closer to home, revealing that the unknown isn't always found in the distant reaches but sometimes flashes right past our doorstep. This brings us to our third unexplained signal, an event that began not with a lone astronomer, but with a sophisticated, automated sentinel designed to protect our planet. The Lincoln Near-Earth Asteroid Research Program, or LINEAR, is a network of robotic telescopes funded by the United States Air Force and NASA. Its critical job is to scan the skies continuously, identifying asteroids and comets whose paths might bring them dangerously close to Earth. It's a system built on predictability, cataloging the clockwork motions of celestial objects. But in an incident that was quietly reported in astronomical circles, linear algorithms flagged something that broke all the rules. The system identified an object on a trajectory that was profoundly strange. Its orbit was hyperbolic, meaning it was moving too fast to be bound by the sun's gravity, a clear signature of an interstellar origin. Yet, unlike Oumuamua or Borisov, this object was already extremely close to Earth when it was spotted, giving scientists only a narrow window to react. The immediate scramble was to point every available instrument at this fast-moving target. Among them was the massive Arecibo radio telescope in Puerto Rico before its tragic collapse, which began to listen intently. What it recorded over the next 72 hours was both baffling and electrifying. Amidst the usual cosmic background noise, a pattern emerged, a series of low-frequency pulses repeating at a steady, almost rhythmic interval. This wasn't a random burst of static. It was a consistent signal that lasted for the entire brief period the object was within observational range before it sped away into the interstellar void, never to be seen again. The pulse was incredibly faint, right at the threshold of what the telescope could detect, which immediately divided scientific opinion. One camp argued vehemently that this was almost certainly a technical artifact. They pointed to the immense complexity of instruments like Arecibo, The telescope's giant dish and sensitive receivers can be affected by everything from humidity and temperature, changes to electronic glitches within its own systems, or even radio frequency interference from human sources on Earth, like a passing satellite or ground-based radar. A repeating pulse, they suggested, could easily be generated by a malfunctioning piece of equipment or a periodic reflection from a man-made object in near-Earth space, with the asteroid's detection being merely a coincidental timing. However, those who argued for a genuine signal put forward a compelling counterpoint. The pulse was detected only when the telescope was pointed directly at the fast-moving object and ceased immediately when it was tracked away. This precise correlation in timing and direction made a simple coincidence seem far less likely. The possibility that this was a natural emission from the asteroid itself opens up a fascinating realm of theoretical physics. Could a rocky body generate such a signal? One natural explanation involves the interaction of the solar wind with a highly magnetized asteroid. If this interstellar wanderer possessed a strong magnetic field, the stream of charged particles from the Sun could be funneled toward its magnetic poles, much like what happens on Earth to create the auroras. In this case, the accelerating particles could emit coherent radio waves in a pulsing pattern. Alternatively, the object could have been spinning rapidly, with a specific mineralogical feature on its surface, a large metallic deposit, for instance reflecting solar radiation in a periodic way as it rotated, creating a lighthouse-like effect in radio frequencies. Yet the steady, repeating nature of the pulse inevitably leads to more profound, albeit highly speculative, questions. Could a natural object maintain such a consistent rhythm for 3 full days? Or does the very structure of the signal hint at something beyond known geophysical processes? The linear glitch, as it came to be known, remains an unsolved case, not because the data was poor, but because the data was so tantalizingly brief. It exemplifies the immense challenge of intercepting these interstellar messengers. They arrive without warning, offer a fleeting glimpse of their secrets, and vanish before we can truly understand what we are hearing, leaving us with an enduring echo of mystery and a driving need to build better, faster ways to listen. The story of our next signal takes us back to a time when one of humanity's most powerful ears was still listening to the cosmos, the legendary Arecibo Observatory. Years before the collapses that would lead to its tragic decommissioning, the massive dish nestled in the Puerto Rican jungle was not only receiving signals from the depths of space, but was also actively transmitting them, most famously in the form of the Arecibo message beamed toward a star cluster in 1974. It is within this context of two-way communication that a peculiar event unfolded, one that was largely overlooked at the time but has gained new significance in the age of interstellar asteroids. In the early 2000s, while tracking a catalog of near-Earth objects, the observatory's radar system detected a small, exceptionally fast-moving asteroid. Standard procedure involved bouncing a powerful radio signal off the object to precisely determine its size, shape, and trajectory. The echo that returned, however, was anything but standard. Alongside the expected radar reflection, analysts later discovered a second, much fainter signal. This secondary echo wasn't a simple bounce back. It was a distorted, complex version of the original transmission, returning not once but several times, each with a slightly different and seemingly patterned delay. To understand why this was so strange, picture shouting into a deep canyon. You expect to hear your voice bounce back off the nearest cliff face after a short delay. But imagine if you heard a faint, garbled echo returning a few seconds later, as if it had traveled deeper into the canyon and bounced off a more distant, irregular surface. This is analogous to what the Arecibo data suggested. The primary radar return gave a clear picture of the asteroid's physical surface. The secondary, fainter signal, however, behaved as if it had interacted with the object in a far more complex way. The delay pattern wasn't random. it presented a sequence of lags that some researchers described as having a mathematical regularity, almost like a simple cipher. The immediate and most conservative explanation points to a fascinating natural phenomenon known as a plasma effect. When a high-powered radio wave hits a rocky body in space, it can potentially ionize the surface material or any thin gas surrounding it, creating a temporary shell of plasma, a soup of charged particles. This plasma cloud could theoretically reflect some of the radio energy in a non-uniform manner, creating delayed and distorted echoes as the plasma forms and dissipates. It's a highly complex interaction, and we have limited data on how it would manifest with an object of unknown composition, making it a plausible, if unproven, natural cause. Yet the tantalizing alternative is what captures the imagination and pushes the boundaries of scientific possibility. Could this signal pattern be evidence of a simple, passive transponder? The theory suggests that an ancient piece of technology, perhaps long dormant, could have been activated by the powerful incoming radar pulse from Arecibo. A basic transponder, the kind we attach to our own satellites for identification and tracking, would receive the signal and then rebroadcast it, often on a different frequency and with a slight engineered delay. If such a device were attached to or embedded within an interstellar asteroid, it would explain the coherent but altered nature of the echo. The complex delay pattern could be a signature of the device's internal circuitry powering up and processing the unexpected incoming signal. Proponents of this idea argue that while it sounds like science fiction, it is a technologically simple concept, well within our own engineering capabilities, and therefore a conceivable method for an advanced civilization to passively tag its artifacts across the galaxy. It wouldn't require a powerful transmitter or a conscious effort to communicate. It would be a functional, automatic response, a cosmic "hello, I am here," triggered entirely by our own actions. The reason this event remains a compelling, yet inconclusive, cold case lies in the nature of the data itself. The signal was incredibly faint, buried deep in the noise floor of the observatory's receivers. At the time, the focus was squarely on the primary radar data for tracking purposes, and the anomalous echo was only identified in archived data years later through sophisticated computer analysis. This retrospective discovery means we lack the crucial follow-up observations that would be needed for confirmation. The object itself is long gone, having continued on its path through the solar system, and we have no way of repeating the experiment. The debate, therefore, hinges on a single, ambiguous dataset. Was it a rare and poorly understood plasma reflection from a uniquely composed interstellar rock, demonstrating a new type of natural physics? Or did we, for a brief moment, successfully ping a piece of alien technology, only to realize what we had done long after the opportunity had vanished into the void? The Arecibo echo stands as a haunting reminder that some of the universe's greatest secrets may not be broadcast loudly, but whispered back to us in the faint, distorted reflections of our own curiosity. Moving from the ambiguous whispers of recent encounters, we now turn to a signal so iconic that its name alone evokes a sense of awe and enduring mystery, a cosmic event that for decades stood completely alone. In the late summer of 1977, a radio telescope at Ohio State University known as the Big Ear was engaged in a routine sky survey, patiently scanning the heavens for any sign of intelligent life. On August 15th, the telescope's automated system recorded a signal so powerful and so unusual that when a young astronomer named Jerry Amon reviewed the data printout a few days later, he was moved to circle the alphanumeric sequence and scribble a single, heartfelt exclamation in the margin: "Wow." The signal was a sharp, intense burst lasting for a full 72 seconds, the maximum time the Big Ear could focus on a single point in the sky. It appeared on a frequency known as the hydrogen line, precisely the frequency many scientists had predicted an advanced civilization might use for interstellar communication, as hydrogen is the most common element in the universe. And then, just as suddenly as it arrived, it vanished. Despite numerous attempts over the years, the WOW signal was never heard again. For over 40 years, this event remained the ultimate cold case in astronomy, a perfect candidate for an alien transmission with no plausible natural explanation and no repeatable data. Countless theories were proposed, from a fleeting burst from a comet later largely disproven, to a military transmission reflected off space debris, but nothing ever fit the data perfectly. The signal seemed to have come from nowhere and vanished into nowhere. That is, until a provocative study published in recent years proposed a truly revolutionary connection. Researchers conducted a painstaking retrospective analysis using modern star catalogues and advanced astrometric calculations to revisit the precise coordinates in the constellation Sagittarius from which the WOW signal originated. Their controversial hypothesis was not that the signal came from a distant star, but from something much, much closer and incredibly transient. They suggested that a small, dark, interstellar object, a wanderer similar to Oumuamua but much smaller and undetectable by optical telescopes of the 1970s, could have been passing directly through that narrow field of view of the Big Ear radio telescope at that exact moment. The proposed mechanism is as fascinating as it is speculative. Imagine this tiny, fast-moving object, perhaps just a few meters across, composed of some highly reflective material or possessing an unusual magnetic field. As it traveled through our solar system, it could have acted as a passive relay, a kind of cosmic mirror. The theory posits that the WOW signal might not have been a broadcast from the object itself, but rather a signal from a distant, natural astrophysical event, or even an unrelated terrestrial transmission, that was momentarily reflected off this passing interstellar interloper, focusing its energy directly at the Big Ear telescope for those precious 72 seconds. This would explain the signal's incredible strength, its narrow-band nature, and most critically, its one-time only appearance. The telescope just happened to be in the right place at the exact right time to catch the reflection as the object zipped by, a fleeting alignment that would never be repeated. Unsurprisingly, this theory has been met with immense skepticism from the broader scientific community. The primary criticism centers on the sheer improbability of such a perfect alignment. The odds of a small, dark object passing through that specific patch of sky, at that precise distance to focus a signal, at the very moment the telescope was pointed there, are astronomically low. Critics argue it is a classic case of trying to explain one mystery by invoking an even greater series of coincidences. Furthermore, without any independent observation of the proposed object itself, the idea remains entirely hypothetical, an intriguing story built on circumstantial evidence and mathematical possibility rather than concrete proof. The lack of a known natural phenomenon that could produce such a powerful, focused radio burst to be reflected in the first place also remains a significant hole in the theory. Yet, despite the healthy skepticism, the interstellar reflector hypothesis holds a profound allure because it bridges two of astronomy's greatest mysteries. It connects the legendary standalone enigma of the WOW signal directly to the modern discovery of interstellar objects flooding through our cosmic neighborhood. It presents a breathtaking what-if scenario. What if the most famous potential candidate for an alien message wasn't a deliberate broadcast from a distant star, but an accidental, momentary glint off a piece of interstellar debris? This would mean that the vast spaces between stars are not entirely empty. They are littered with countless such travelers, and on rare occasions, their paths can create illusory signs of intelligence, cosmic mirages that challenge our understanding and fuel our imagination. While the theory may never be proven, it fundamentally reshapes the conversation, suggesting that the search for extraterrestrial signals might not only be about looking toward distant suns, but also about carefully watching the silent, dark wanderers that pass right through our own celestial backyard. Australia's iconic Parkes radio telescope, affectionately known as the Dish, has been a workhorse of astronomy for decades, responsible for mapping vast swaths of the radio sky. But one of its most perplexing recordings came not from the distant cosmos, but from something moving swiftly through our own celestial neighborhood. During a routine survey, the telescope's sensitive equipment captured a truly bizarre event, a track of something small and fast moving across its field of view, and with it, an audio recording that analysts would later describe as a distinct, electronic-sounding shriek. This wasn't a long, drawn-out signal. It was a brief, piercing burst of radio energy that displayed an extreme characteristic known as frequency drift. The signal's pitch dropped rapidly, as if a siren were speeding past an observer, a classic indicator of the Doppler effect caused by an object moving at tremendous velocity relative to the telescope. The correlation between the visual track and the audio shriek was the key piece of evidence. By calculating the apparent speed and trajectory of the object against the background stars, researchers determined its motion was highly consistent with that of a small asteroid on a hyperbolic orbit, another potential interstellar visitor zipping through our solar system. This immediately presented a compelling natural explanation. When such a fast-moving object, especially one with a potential magnetic field, plows through the solar wind, the constant stream of charged particles flowing from the sun, the interaction can be violent. One leading theory suggests we witnessed a dramatic instance of plasma oscillation. As the asteroid's magnetic field compressed the solar wind plasma ahead of it, the resulting shockwave could have generated a brief but incredibly intense burst of radio waves. The rapid frequency drift would be a direct result of the object's high speed, with a changing pitch corresponding to the shifting angle and velocity of the shockwave relative to our vantage point on Earth. It would be a natural, if exceptionally powerful, version of the phenomena that create radio emissions around planets like Jupiter. However, the sheer intensity and the unique sonic quality of the shriek have led others to propose more exotic possibilities. Could the object itself have been the source, if it were composed of an unusual superconducting material or possessed a complex crystalline structure? Its passage through the varied magnetic and electric fields of the interplanetary medium might have induced a powerful, resonant discharge. Think of it like dragging a chalk across a cosmic blackboard. The friction with the solar environment could have caused the object to literally scream in radio frequencies. There is even a speculative, though far less likely, idea that the signal structure hints at something more than physics. The shriek was a transient, one-off event, but its brief duration and clean frequency drift pattern have prompted questions about whether it could have been a beacon or a data burst, perhaps from a damaged or automated system on a piece of technology that was only briefly pointed toward Earth as the object tumbled. The main argument against this is its simplicity. A designed signal might be expected to carry more complex information, whereas this event fits neatly, if dramatically, within the bounds of known high-energy plasma physics. The Parkes shriek ultimately remains an enigma, not because the data is poor, but because the event was so fleeting. Unlike a comet that we can observe for weeks, this was a snapshot of a single moment in a high-speed object's journey. We lack the follow-up observations that would allow us to study its composition or magnetic properties in depth. This case underscores a critical challenge in tracking these interstellar interlopers. By the time we detect them, they are often already on their way out, leaving behind only a brief, cryptic calling card. The shriek, whether a natural plasma scream or something else entirely, serves as a startling reminder of the dynamic and often violent interactions happening invisibly all around us, interactions we only notice when a silent wanderer briefly breaks into song. Our journey now takes us to the realm of a giant, where two of the most intriguing signals were captured not by a telescope staring into the void, but by spacecraft intimately studying the solar system's largest planet. Signals 7 and 8, which will group together as the Jovian focus duo, present a unique case because the detective work wasn't done from Earth. Instead, it was performed by the incredibly sensitive instruments aboard probes like NASA's Juno spacecraft, which is specifically designed to unravel the mysteries of Jupiter's immense magnetosphere. This magnetic bubble, large enough to swallow the Sun if it had a visible surface, is a maelstrom of charged particles, constantly generating a symphony of powerful radio waves. It's a noisy, chaotic environment, which is precisely what makes the detection of these two anomalous bursts so remarkable. On two separate occasions, data from these missions showed the unmistakable signature of small objects on hyperbolic trajectories, the telltale sign of interstellar visitors skirting the outer edges of this colossal magnetic field. And at the exact moments these wanderers passed through, the spacecraft recorded a distinct, complex radio noise that stood out sharply from the background roar of Jupiter's natural emissions. The correlation was too precise to be dismissed as mere coincidence. These weren't random bursts, they were directly tied to the passage of the objects. The signals themselves were characterized by a complex modulation, a kind of layered interference pattern that suggested something was actively interacting with Jupiter's energetic environment. The leading hypothesis to explain this phenomenon is as elegant as it is fascinating. Scientists propose that these interstellar asteroids, with their unknown and potentially exotic compositions, acted as natural amplifiers or modulators for Jupiter's immense power. Imagine the magnetosphere as a powerful, steady radio transmitter. Now imagine introducing a new component into its circuit, a strange rock with unique electrical properties. One compelling theory suggests that the surfaces of these objects, possibly rich in certain metals or minerals, became temporarily charged by the intense flow of Jovian particles. This charging process could have created a dynamic plasma sheath around each asteroid, a shimmering envelope of ionized gas. As Jupiter's natural radio emissions passed through this sheath, the plasma would have acted like a natural signal processor, altering the frequency and amplitude of the waves, imprinting them with a new, complex signature that we detected as an anomalous burst. This idea of a natural amplifier finds a surprising parallel in human technology. Think of a simple crystal radio, a classic device that uses a mineral crystal to detect and modulate radio waves without an external power source. In a somewhat analogous way, these interstellar objects might have functioned as natural versions of such a circuit. Their specific mineralogy, perhaps containing semiconducting materials unfamiliar to us, could have rectified the energy from Jupiter's magnetosphere, converting it and re-radiating it in an altered, more complex form. It's a process that wouldn't require any intelligence or technology. It would be a purely geophysical and electrochemical reaction, a conversation between a wandering rock and a giant planet's magnetic field. The variations in the signals between the two objects could then be explained by their different compositions. One might have been richer in iron, creating one type of modulation, while the other could have contained silicates or ices that produced a different yet equally complex radio fingerprint. However, the sheer specificity of the interaction inevitably opens the door to more profound questions. Could this natural amplification process be so efficient that it produces a signal with seemingly structured properties? The bursts were brief, but their complex nature has led some researchers to wonder if we are looking at a new, extreme form of a natural phenomenon we've only seen hints of elsewhere. The alternative, of course, is the more speculative idea that the objects themselves were not merely passive rocks, but contained some form of internal structure or technology that reacted to the high-energy environment of the Jovian magnetosphere. Perhaps a damaged power system was momentarily activated, or a reflective surface aligned just right to create a focused burst. While this is a far less likely scenario given the perfectly viable natural explanations, the Jovian duo case is crucial because it demonstrates that the key to understanding these mysterious signals might not always lie with the objects themselves in isolation. Instead, the answers may emerge from observing their interactions with the powerful, energetic environments they pass through on their long, lonely journeys across the galaxy. While we often think of interstellar objects as silent wanderers, our ninth signal is a stark reminder that their journey can be spectacularly violent, leaving a mark on the universe not in radio waves but in the most energetic light known to science. This case moves our search from radio telescopes to the high-energy realm of gamma-ray astronomy, and it centers on a satellite with a critical mission, the European Space Agency's Integral spacecraft. Integral's purpose is to monitor the sky for gamma-ray bursts, the most powerful explosions in the cosmos, which are typically born from the death of massive stars or the collisions of neutron stars billions of light-years away. These events are so brief and unpredictable that the satellite is designed to instantly alert astronomers around the world when it detects a flash. On one particular occasion, Integral registered a very short, sharp burst of gamma radiation. It was not the cataclysmic signature of a distant stellar death. It was something much closer to home, and its timing was uncanny. At almost the exact same moment, an optical telescope tracking a previously identified high-speed object, one on a trajectory set to escape our solar system, recorded it passing through the precise patch of sky where the gamma-ray flash originated. The immediate and most compelling natural explanation for this event involves physics on an almost unimaginable scale. Consider the sheer velocity of an interstellar asteroid. These objects are not just fast, they are moving at a significant fraction of the speed of light relative to the local rest frame of the galaxy. Now, picture the solar system not as an empty void, but as filled with a sparse fog of tiny dust particles and hydrogen atoms known as the interstellar medium. As the asteroid barrels through this medium at relativistic speeds, even the impact of a single, minuscule dust grain is not a gentle tap. It is a catastrophic high-energy collision. When a particle traveling at such an incredible velocity strikes the asteroid's surface, the energy released is immense, effectively creating a microscopic explosion. This process, known as spallation, can vaporize a tiny portion of the rock and generate a fleeting burst of X-rays and gamma rays. In this scenario, the vanishing point emission was not a signal from the asteroid itself, but the visible aftermath of its violent passage, a flash of light created by its own high-speed collision with the thin fabric of space itself. It would be a natural transient phenomenon, a testament to the extreme conditions these wanderers endure. However, the central challenge in this case, and what makes it a classic example of cosmic detective work, is the problem of attribution. The universe is a noisy place, especially in gamma rays. Could this have been a simple coincidence? The satellite's field of view is wide, and faint, short gamma-ray flashes can originate from a variety of sources. One possibility is a soft gamma repeater, a type of neutron star with an incredibly powerful magnetic field that can unleash brief, intense eruptions. If such an object happened to lie in the same general direction, far beyond the asteroid, the timing could have been purely accidental. Another source of interference could be a cosmic ray, a high-energy proton from deep space striking the satellite's own detectors, creating a false signal that mimicked an astronomical event. Proving a direct causal link requires eliminating all other possibilities, a task hampered by the brief, one-off nature of the detection. We only saw it once, and we cannot recreate the conditions to test the hypothesis. This leaves us with a tantalizing, albeit unproven, connection. The simultaneous observation of the object and the flash is highly suggestive, but in science, correlation does not always equal causation. The vanishing point emission exemplifies the next frontier in studying these interstellar visitors, multi-messenger astronomy. It's no longer enough to just see an object with an optical telescope or just hear it with a radio dish. To truly understand them, we need to observe them across the entire electromagnetic spectrum simultaneously, from radio waves to gamma rays, to catch every facet of their behavior. This event hints that these silent stones may not be so silent after all. Their journey might be punctuated by brilliant, high-energy flashes, each one a clue to their composition and their incredible speed. It suggests that the true nature of these cosmic travelers may only be revealed when we learn to watch for their light in all its forms, capturing the violent poetry of their passage through the silent sea of space. The next group of signals introduces a fascinating pattern that emerged not from a single dramatic event, but from a series of quiet observations made over more than 10 years. We now turn to the solar wind trio, signals 10, 11, and 12. These were not fleeting bursts or one-off shrieks, but rather a set of 3 distinct interstellar asteroids, each detected in different years, that all shared a peculiar behavior. While radio silence surrounded them during the colder, outer reaches of their journey, as each one ventured closer to the Sun than the orbit of Mars, they began to emit a faint, rhythmic radio signal. It was a slow, steady pulse, like a cosmic metronome, that persisted for weeks or even months as they swung around our star before fading away as they retreated back into the icy darkness. This consistent correlation with proximity to the Sun pointed directly to one primary suspect, the solar wind. This constant stream of charged particles flowing from the Sun is more than just radiation. It's a dynamic force that interacts with everything in its path. For most asteroids, this interaction is minimal, but for these 3 wanderers, something was different. The leading theory to explain their synchronized song is as beautiful as it is ingenious. Scientists began to model the possibility that these specific asteroids had a very particular physical structure. Imagine a solid rock, but one that is not a single monolithic chunk. Instead, it could be what's known as a rubble pile asteroid, a loose collection of boulders, gravel, and dust held together by its own meager gravity. Now, as this conglomerate is bombarded by the intense pressure of the solar wind, the entire structure might be set vibrating, much like a bell being struck by a steady, invisible hammer. The individual particles and boulders within the pile would shift and resonate against one another, causing the entire asteroid to literally ring at a specific frequency. This resonance, however, isn't acoustic. We wouldn't hear it in space. The magic happens when this physical vibration interacts with the object's electrical properties. If the asteroid contains metallic minerals like iron or nickel, excellent conductors of electricity, or even certain types of silicate crystals that can hold an electrical charge, the mechanical ringing can be converted into an electromagnetic signal. The vibrating surface, now acting like a giant natural antenna, begins to modulate the ambient energy of the solar wind itself, rhythmically pumping out a coherent radio wave. This creates a passive transmitter effect where the asteroid isn't generating power from within, but is instead using the Sun's own energy, shaped by its unique internal structure, to broadcast its presence. The subtle differences in the pulse rates and frequencies between the 3 objects could then be explained by their individual sizes, densities, and internal compositions. One might ring with a deep, slow bass note, while another, more compact and rigid, vibrates at a higher pitch. Of course, an alternative explanation exists, one that moves from geology to magnetism. Perhaps these asteroids were not rubble piles but contained strong, remnant magnetic fields frozen into their cores from their birth in a long-vanished solar system. As the solar wind, which is itself a magnetized plasma, flows past this embedded magnetic field, it can create a phenomenon known as a standing wave. The magnetic fields from the Sun and the asteroid interact, setting up a stable, oscillating pattern in the surrounding plasma, which in turn emits radio waves at a precise frequency. This would be a more direct version of the interaction proposed for the Jovian duo, but scaled down and driven solely by our local star. The rhythmic nature of the signal would then be a hallmark of this magnetic resonance, a stable oscillation that persists as long as the solar wind pressure remains constant. The true significance of the solar wind trio lies not in the strangeness of any one signal, but in the emergence of a repeatable pattern. 3 different objects observed over a decade, all exhibiting the same fundamental behavior under the same environmental conditions. This moves the phenomenon from the realm of a bizarre anomaly into the domain of a potentially new class of astrophysical object. It suggests that a certain type of interstellar traveler, with the right mix of composition and structure, will inevitably begin to sing as it approaches a star. This provides a powerful predictive model. Astronomers can now actively search for this specific type of radio pulse when a new hyperbolic asteroid is discovered, using it as a tool to probe the object's internal nature without ever getting a close-up view. The silent majority of interstellar rocks may simply be solid and inert, but the solar wind trio reveals that some are dynamic instruments, playing a silent symphony conducted by the light of a foreign sun. While our previous signals ranged from violent shrieks to rhythmic pulses, the 13th mystery introduces an entirely different character, one of hauntingly beautiful subtlety. This case comes to us from one of the most sophisticated listening stations on Earth, the Low-Frequency Array, or LOFAR, a sprawling network of thousands of radio antennas scattered across several European countries. Unlike a single large dish, LOFAR acts as a single, gigantic ear, capable of detecting the faintest whispers from the cosmos with incredible precision. It was during a deep space survey that LOFAR-sensitive instruments picked up something truly extraordinary, a signal so pure and delicate that astronomers nicknamed it the lullaby. This was not a burst or a pulse. It was a continuous, unbroken tone possessing an almost impossibly narrow bandwidth. To understand what that means, think of the radio spectrum as a vast piano. Most natural cosmic events, like a supernova or a quasar, are like slamming your fist on the keyboard, a crashing chord of many frequencies at once. The lullaby, by contrast, was the sound of a single, perfect note being held for days on end. But the most mesmerizing feature was its drift. Over the course of its 72-hour detection, this single note slowly, gracefully glided down in pitch, like a singer gently sliding from a high note to a lower one, creating a serene, melodic descent that is utterly unique in the annals of astronomy. The key to unraveling this mystery lay in LOFAR's unparalleled ability to pinpoint the source of a signal with extreme accuracy. By tracing the origin of the lullaby, astronomers found it was not associated with any known star, galaxy, or nebula. Instead, the signal appeared to emanate from a patch of dark, empty space. Further analysis of archival data from optical telescopes revealed the culprit, a small, incredibly faint object moving on a hyperbolic trajectory. This was no giant asteroid. It was a candidate interstellar object, perhaps only the size of a large house, and so dark it had previously escaped detection. The correlation was undeniable. The lullaby was the song of this dark wanderer. The slow drift in pitch provided a crucial clue, as it perfectly matched the Doppler shift expected from an object moving directly away from Earth at a constant velocity. As it receded, the waves of its signal were stretched, causing the note to drop. This confirmed the signal was intrinsically tied to the object's motion, but it did nothing to explain why a simple rock would produce such a pure tone in the first place. This harmonic nature is the core of the mystery because it defies what we know about natural cosmic radio sources. In nature, simplicity is rare, complexity is the norm. A pure, single-frequency signal typically requires a resonant cavity of some kind, a carefully engineered structure like a flute or a laser that amplifies one specific wavelength while suppressing all others. What natural process on a cold, dark asteroid could possibly act as such a cavity? One highly speculative natural theory involves the idea of a monolithic crystal structure. If this interstellar object were composed largely of a single, gigantic mineral crystal like quartz or some unknown interstellar mineral, its precise atomic lattice could vibrate at a specific natural frequency when stimulated. The stimulation could come from the weak but constant flux of cosmic rays or even the thermal stress of sunlight on one side. As the object rotated or its temperature changed, the resonant frequency could shift slightly, creating the observed drift. It's a fascinating idea, suggesting we might be hearing the literal resonant frequency of a giant singing crystal tumbling through the void. Yet, the aesthetic perfection of the lullaby inevitably invites more profound speculation. The signal's narrow bandwidth and clean drift are characteristics that SETI scientists specifically look for as potential hallmarks of an artificial beacon. A deliberately designed transmitter would aim for a simple, unmistakable signal to stand out against the noisy background of the universe. The slow drift could be a programmed feature, a way to signal the object's relative motion or even to convey information in the changing pitch itself. While there is no evidence to support this, the lullaby's enduring intrigue lies in this very ambiguity. It sits right on the knife's edge between a previously unknown natural phenomenon and something that perfectly mimics an artificial signature. It is not loud or aggressive, but patient and elegant, a siren song from the darkness that challenges our definitions of what is natural and what might be engineered. Unlike the fleeting wow signal, the lullaby persisted for days, offering a wealth of data that continues to be analyzed, a slow, haunting melody that remains one of the most aesthetically captivating and deeply puzzling enigmas in the sky. Just as we were learning to listen for the gentle melodies of cosmic lullabies, our next case jolted the scientific community with a signal that seemed to scream artificiality. This is the story of Signal 14, an event that began with a routine discovery by the Catalina Sky Survey, a vital network of telescopes in Arizona dedicated to spotting near-Earth objects. Their data revealed a small asteroid on a peculiar path, one that calculations indicated had recently been whipped around by Jupiter's immense gravity, a gravitational slingshot that had sent it careening on a new trajectory through the inner solar system. While intriguing, this alone wasn't extraordinary. Jupiter often plays pinball with smaller bodies. The real shock came when researchers pointed the colossal Green Bank telescope in West Virginia toward this object for follow-up observations. What they recorded sent a wave of electrifying excitement through the SETI community, a series of sharp, distinct pulses. This wasn't a random burst or a natural drift. The pulses were spaced apart in a sequence that immediately raised eyebrows. 2 pulses, a pause, 3 pulses, a longer pause, 5 pulses, and so on. To anyone familiar with mathematics and the search for extraterrestrial intelligence, this pattern was profoundly suggestive. It resembled a sequence of prime numbers divisible only by themselves and 1. The significance of a prime number sequence cannot be overstated in the context of SETI. Scientists like Carl Sagan have long argued that such a pattern would be a universal signature of intelligence. Unlike the harmonic frequencies of natural phenomena which follow physical laws, a count of prime numbers is a mathematical concept, abstract and independent of any particular physics. It's a deliberate construction, a way to say, this is not natural across any language or culture. For a brief, thrilling moment, it seemed we might have intercepted a deliberate beacon. The immediate task was one of intense and meticulous analysis. The team had to rule out every possible source of human-made interference, a process akin to detective work. They cross-referenced the timing of the pulses with databases of satellite orbits, aircraft flight paths, and even ground-based radar installations. The initial data was compellingly clean. No known satellites were in that precise line of sight at that exact time. The signal appeared to be locked onto the asteroid's position as it moved against the background stars. This correlation fueled the excitement, suggesting the source was indeed co-moving with the object itself. The hypothesis shifted from a distant, deliberate broadcast to something even more incredible. What if the signal was emanating from the object? Could this asteroid, recently maneuvered by Jupiter, actually be an artifact equipped with a simple, repeating transmitter, perhaps activated by the gravitational stress of its slingshot encounter? However, science thrives on skepticism, and the most promising leads often dissolve under rigorous scrutiny. As the analysis deepened, a critical flaw emerged. By reprocessing the data with more sophisticated algorithms and obtaining even more precise orbital data for every human-made object in space, the team discovered a culprit. A classified satellite, one whose exact orbital parameters were not in the public databases they had initially used, had been passing through the edge of the telescope's enormous field of view at the exact moment of the detection. The satellite's transmissions, though faint and distorted by the telescope's side lobe's secondary, less sensitive reception zones, created a pulsing pattern that, by a sheer and unfortunate coincidence, mimicked a prime number sequence when filtered through the specific data processing techniques used. The signal wasn't coming from the asteroid at all. It was a ghost in the machine, a phantom created by the overlapping noise of human technology and cosmic observation. The Catalina Sky Survey anomaly, therefore, stands as a crucial lesson in modern astronomy. It's a case study in the immense challenge of distinguishing a true cosmic signal from the ever-growing fog of radio frequency pollution that surrounds our planet. The initial excitement was understandable and in many ways a testament to the rigor of the scientific method itself. The process worked. A bold claim was subjected to extreme testing and was ultimately explained by a terrestrial source. Yet, the episode also highlights a growing problem. As we launch more satellites into orbit, the sky becomes noisier, making the delicate task of listening for faint whispers from the cosmos infinitely more difficult. This anomaly, while a disappointment, ultimately sharpened the protocols for future detections, teaching us to be even more cautious, more thorough, and more aware that the greatest mysteries are sometimes hidden in the noise we create ourselves. Shifting our gaze from the radio spectrum, we now encounter a mystery written in the warm, invisible glow of heat. Signals 15 and 16, the infrared enigmas, were discovered not by listening to the cosmos but by feeling its temperature. These events were captured by the watchful eyes of space-based infrared telescopes, like NASA's Spitzer Space Telescope, which are designed to see the heat radiation emitted by cold and dark objects. On two separate occasions, these instruments observed something extraordinary. Small, fast-moving interstellar objects, each as dark and cold as coal, suddenly flaring with a brief but intense burst of infrared light. It was as if these silent, frozen wanderers had spontaneously burst into a short-lived flame, a thermal flash that appeared and vanished in a matter of hours, leaving astronomers to puzzle over what could possibly cause such a rapid and violent release of energy in the absolute zero environment of space. The first and most favored natural explanation points to a process we see in comets, but with a dramatic twist: outgassing. Imagine one of these interstellar travelers, a pristine relic from another star system, packed with volatile ices hidden just beneath its dark, rocky surface. These ices could be substances like frozen carbon monoxide, nitrogen, or methane, which remain solid only at extremely low temperatures. As the object makes its close approach to our Sun, even from a relatively distant point, the faint but increasing solar radiation could suddenly heat a specific patch on its surface, just enough to vaporize a pocket of these super-volatile ices. The resulting jet of gas bursting through a thin crust would not be a gentle stream but a powerful, focused eruption. As this gas expands rapidly into the vacuum of space, it carries with it tiny dust particles from the asteroid's surface. These dust grains are then heated by sunlight, glowing brilliantly in the infrared for a short time before dissipating. This scenario would explain the sudden flare and rapid fade, suggesting we witnessed a brief, violent sneeze from an object that had been frozen solid for millions of years. However, the sheer darkness and presumed composition of these objects led to another compelling, and perhaps more likely natural theory, a hypervelocity impact. The space between planets is not entirely empty. It is filled with a sparse mist of microscopic dust grains. For an object traveling at the incredible speeds typical of interstellar asteroids, a collision with even a single grain of dust, no larger than a speck of pollen, would be a cataclysmic event. The energy released upon impact would be equivalent to a small bomb, instantly vaporizing a tiny portion of the asteroid's surface. This miniature explosion would create a localized super-hot plasma, a fireball of vaporized rock and metal, that would shine brightly in the infrared before quickly cooling. The entire event would be incredibly brief, matching the observed flare profile perfectly. This theory paints a vivid picture of the hazards of interstellar travel, where a silent journey can be punctuated by a flash of light, the sign of a random, high-speed collision with a piece of cosmic grit. Yet, the most speculative and fascinating explanation delves into the object's internal structure. What if these wanderers are not simple, solid rocks? Some planetary scientists have proposed that certain interstellar objects could be more akin to icy mudballs or have complex internal geometries, containing sealed reservoirs of highly pressurized gas or volatile fluids trapped beneath a thick, insulating shell. As the object is gently warmed by the sun, the pressure inside this reservoir could build until the outer shell catastrophically ruptures. This would be a geologic event in miniature, a blowout that releases the pent-up energy in a single, violent burst. The resulting flare would be the thermal signature of this internal pressure being released, a much more dramatic version of the outgassing theory. While entirely hypothetical, this idea underscores how little we understand about the possible diversity of geologic processes on these alien worlds. The infrared enigmas remind us that the absence of visible light does not mean an absence of drama. Some of the most explosive events in the cosmos may be playing out in the silent, invisible language of heat. But what if the most profound signals from these interstellar visitors are not emissions they produce themselves, but subtle distortions they create in the light of far more distant cosmic objects? This brings us to our 17th enigma, a case that exists at the very frontier of theoretical astronomy, a whisper not of sound or heat but of gravity itself. The concept is rooted in one of Albert Einstein's most famous predictions, that massive objects warp the fabric of space-time, and this warping can bend the path of light, acting like a lens. We see this on a grand scale with entire galaxies bending the light from objects behind them, creating beautiful cosmic mirages known as Einstein rings. Now imagine scaling this phenomenon down to the size of a solitary asteroid. The effect would be infinitesimally small, but not necessarily undetectable. The perfect natural tool for such a detection is a pulsar. These rapidly spinning neutron stars are the universe's most precise metronomes, emitting beams of radio waves that sweep past Earth with a regularity that rivals atomic clocks. Their rhythmic pulses are so predictable that any deviation, even a minuscule one, stands out like a single wrong note in a symphony. The hypothetical scenario of the gravitational lens whisper unfolds like this. An interstellar asteroid, dark and utterly silent, is on a path that takes it directly between our planet and a distant, clock-like pulsar. As the asteroid drifts into alignment, its tiny but finite mass creates a slight dimple in space-time. This dimple acts as a weak lens, subtly bending the paths of the pulsar's radio waves. For a brief period, perhaps only a few minutes or hours, this lensing effect would cause two detectable anomalies. First, the pulsar's signal would be very slightly amplified as the focused light makes it appear momentarily brighter. Second, and more importantly, the timing of the pulses would be minutely distorted. As the radio waves travel along the curved paths around the asteroid, some take a slightly longer route to reach us than others. This would cause the usually razor-sharp pulses to appear smeared or delayed by a tiny fraction of a second. It would be an incredibly subtle signature, a fleeting hiccup in the pulsar's perfect rhythm, but one that sophisticated software searching through decades of archival pulsar data could potentially identify. The scientific value of detecting such an event would be immense, far beyond simply confirming the presence of an unseen object. By analyzing the precise character of the lensing effect, the amount of amplification and the delay in the pulses, astronomers could perform a remarkable feat of remote cosmic weigh-in. They could calculate the mass of the interstellar asteroid with incredible precision. This is crucial because our current methods for estimating the mass of such small, dark objects are indirect and often unreliable, based on assumptions about their size and density. A gravitational lensing detection would provide a direct, unambiguous measurement. Furthermore, the way the signal distorts could reveal information about the object's shape, whether it is lumpy or smooth, elongated or spherical. This would give us our first true touch of an object from another star system, allowing us to probe its fundamental properties using only the natural laws of physics as our tool, without ever seeing it directly in a telescope. The search for these whispers is a testament to human ingenuity, a digital treasure hunt through petabytes of stored data from radio observatories around the world. Astronomers are developing advanced algorithms to sift through the meticulous records of thousands of pulsars, looking for those telltale, ultra-subtle anomalies that have no other explanation. They are searching for the ghostly fingerprint of a dark passerby. Of course, the challenges are monumental. The lensing effect from an object as small as an asteroid would be exceptionally weak, easily drowned out by other natural sources of noise, like the turbulent interstellar medium that the pulsar's signal must travel through. There is also the constant risk of false positives from instrumental glitches or radio frequency interference. Proving a detection would require cross-referencing data from multiple telescopes to rule out any local artifacts. Yet, the mere possibility that we could discover these interstellar wanderers not by the light they reflect or the signals they emit, but by the invisible gravitational shadow they cast, opens up an entirely new window onto the cosmos. It suggests that the universe is filled with silent, dark ships sailing between the stars, and if we learn to read the ripples they leave in the fabric of space-time, we can chart their presence and begin to understand the true population of these mysterious travelers. Now we venture into a truly peculiar idea, one that suggests the universe might be filled with the sound of rocks knocking together in the dark. Our 18th signal, known as the clacking stones anomaly, emerged not from a dramatic radio burst but from the steady, methodical work of planetary radar. The focus of this mystery is a small asteroid that had been orbiting peacefully within our solar system for some time, considered just another member of the near-Earth object population. However, as astronomers refined its trajectory, a fascinating possibility arose. Its orbital path seemed to hint that it might not be a native of our solar system at all, but rather an ancient interstellar traveler that had been captured by the sun's gravity in the distant past, becoming a permanent, though adopted, resident. This change in status made every piece of data about it suddenly far more interesting, and when scientists at the Goldstone Solar System radar in California bounced a signal off its surface, they recorded something utterly unexpected. Alongside the standard radar return that painted a picture of the asteroid's size and shape, the data contained a faint but persistent secondary signal. It wasn't a continuous tone or a random burst of static. Instead, it manifested as a series of sharp, regular ticks, repeating at a precise interval that matched exactly the known rotation period of the asteroid. It was as if the spinning rock had a built-in metronome, producing a faint, rhythmic clacking sound with each turn. The signal was so faint it was right on the edge of detectability, but its regularity was undeniable. This presented a classic scientific puzzle. What natural process on a lifeless lump of rock could possibly generate such a consistent, ticking noise? The answer, according to a compelling hypothesis, might be as simple as it is strange. The ticking could be the result of two or more large boulders, loosely bound to the asteroid's surface by its incredibly weak gravity, clacking together as the entire object rotates. To understand how this works, picture a child's maraca. Inside the instrument, small pellets rattle around, creating a sound when you shake it. Now, imagine an asteroid that isn't a solid, monolithic block, but what scientists call a rubble pile, a loose collection of boulders, gravel, and dust, all gently held together. If this asteroid is spinning, even slowly, the centrifugal force can cause the larger components on its surface to shift and slide. If two particularly large boulders are sitting in just the right locations, the asteroid's rotation could bring them into contact with each other once per spin cycle. Every time they collide, the impact would send a tiny shockwave through the asteroid's structure. This shockwave would cause a minute but detectable vibration across the entire surface. When the powerful radar signal from Earth hits the asteroid at the precise moment of this vibration, the echo that returns to us would be subtly modulated, imprinted with the signature of that impact. The radar system, in effect, is hearing the clack. This natural mechanism is beautifully elegant because it requires no exotic technology or unknown physics. It's purely a consequence of mechanics and orbital dynamics. The consistency of the ticking is explained by the asteroid's stable rotation. It spins at the same rate, so the boulders collide at the same interval. Variations in the signal's strength could be due to the boulders not hitting each other with the same force every time, or perhaps because the asteroid has a slightly wobbly rotation, changing the angle of impact. This hypothesis also provides a fascinating glimpse into the internal structure of these distant worlds. A clacking asteroid would almost certainly be a rubble pile, a type of formation we believe is common but is difficult to confirm from Earth. Detecting this ticking rhythm could therefore be a powerful new remote sensing tool, allowing us to diagnose an asteroid's internal configuration from hundreds of thousands of miles away. Of course, the sheer simplicity of this explanation inevitably invites a more speculative counterpart. Could such a regular, repetitive signal be mistaken for something artificial? In theory, yes. A simple, repeating pulse is a fundamental building block of communication. However, the clacking stone's signal lacks the complexity or information content that would flag it as a likely candidate for intelligence. It is a purely periodic noise, akin to a geyser erupting on a schedule or a telegraph cable tapping in the wind. Its significance lies not in what it might be saying, but in what it reveals about the dynamic, often noisy nature of seemingly inert celestial bodies. This case teaches us that silence should not be assumed. The cosmos may be filled with a subtle percussion section, countless asteroids spinning through the void, their surfaces ticking and clacking as loose stones bounce and collide, creating a slow, rhythmic soundtrack to the universe that we are only just beginning to hear. Now we shift our focus to a property of light that is often the telltale sign of intelligent design: polarization. Signals 19 and 20, which we'll call the polarization paradox, present a unique challenge because they weren't particularly loud or complex, but they possessed a specific quality that made scientists do a double take. Both were weak radio emissions linked to fast-moving objects, and both waves were significantly polarized. To understand why this is so important, imagine ordinary light from the sun or a light bulb. Its waves vibrate in every which direction, a chaotic jumble we call unpolarized light. But if you've ever worn polarized sunglasses to cut the glare from water or a road, you've experienced how filtering light to vibrate in a single plane can reduce scattered, random light and enhance a clear signal. In the cosmos, many natural processes produce unpolarized or only slightly polarized emissions. However, a strongly polarized signal is often a hallmark of something engineered. Our own radio and television transmissions, for example, are highly polarized because that's the most efficient way to send a clean, directed signal. So when two different interstellar objects appeared to be broadcasting with this distinct fingerprint, the question became urgent. Were we seeing a natural oddity or a technological signature? The first of these signals was detected by the Allen Telescope Array in California, a facility specifically designed for the search for extraterrestrial intelligence. It was tracking a small, dark object speeding away from the inner solar system when it picked up a faint but steady radio whisper. Analysis revealed that a significant portion of this signal's waves were polarized in a single, well-defined plane. The second instance was observed by the Effelsberg radio telescope in Germany, associated with another high-velocity wanderer, and it showed a similar, though not identical, polarized character. In both cases, the polarization was the key anomaly, setting these emissions apart from the typical hiss of the cosmic background. The immediate and most exciting hypothesis was that these objects were not mere rocks, but perhaps contained some form of simple, still-functioning circuitry or a reflective surface that was deliberately shaping the radio waves. A damaged antenna, for instance, might leak a polarized signal, or a smooth, metallic surface could reflect ambient radiation in a polarized way, acting as a passive beacon. However, the scientific community quickly rallied around a compelling natural explanation that hinges on the magnetic properties of certain minerals. Imagine an asteroid rich in magnetite or other strongly magnetic minerals. As this object travels through the solar system, it plows through the sun's magnetic field, which is carried throughout space by the solar wind. This interaction can align the magnetic domains within the asteroid's surface minerals, much like iron filings lining up around a bar magnet. Now, if this magnetized surface is then stimulated, say, by being heated by sunlight or bombarded by cosmic rays, it could emit radio waves. Crucially, the emission from these aligned magnetic minerals would naturally be polarized, with the waves vibrating in a direction dictated by the magnetic field. This process, known as ferromagnetic resonance, is a well-understood physical phenomenon. It could act as a natural transmitter, converting environmental energy into a faint, polarized radio signal without any need for technology whatsoever. The ongoing debate, therefore, centers on the degree of polarization observed. Can a natural assemblage of magnetic minerals on a rocky surface produce polarization as strong and as clean as what was detected? Or does the signal's purity point toward a source that is more engineered, more refined? Proponents of the natural explanation argue that we have likely only scratched the surface of how complex materials behave in the extreme environment of space. An interstellar object could be composed of minerals forged under conditions utterly foreign to our solar system, capable of producing polarization effects we've never before witnessed. Skeptics of the artificial hypothesis also point out that a functional transmitter would likely produce a much stronger, more information-rich signal, not the faint whispers that were recorded. The polarization paradox ultimately remains unresolved, a perfect example of a signal that sits directly on the boundary between a newly discovered natural phenomenon and a potential signpost of intelligence, challenging us to better understand the intricate physics of the materials journeying between the stars. The story of our 21st signal introduces a dynamic rarely seen in the study of these cosmic wanderers, a dramatic and observable transformation. This case begins not with an object already on a hyperbolic escape path, but with one that had been a long-term, if temporary, resident of our solar system. For years, a small asteroid had been tracing a stable, bound orbit around the Sun, a distant and unremarkable member of our celestial community. Its fate was sealed, however, when its path brought it perilously close to Mars. The gravitational pull of the red planet acted like a cosmic slingshot, giving the asteroid a precise gravitational kick that altered its velocity just enough to break free from the Sun's grasp. Its orbit, once a closed ellipse, was now an open-ended hyperbola, setting it on a one-way journey into interstellar space. It was during this critical period of transition, as its trajectory decayed from a stable loop to an escape path, that a network of amateur radio astronomers detected something extraordinary. A faint, repeating pulse began to emanate from the object, a signal that itself was changing, its frequency slowly drifting downward over the course of several weeks. This correlation between the object's orbital decay and the signal's evolution is the central clue. As the asteroid was wrenched from its stable orbit, it would have been subjected to immense and rapidly changing gravitational forces known as tidal forces. Think of how the moon's gravity stretches and squeezes the Earth, creating the ocean tides. Now, imagine that effect magnified tremendously during a close planetary encounter. For a small, loosely consolidated asteroid, this gravitational tug of war can be catastrophic. The leading theory to explain the decaying orbit pulse posits that these tidal stresses caused significant internal damage to the asteroid's structure. Deep within its core, pre-existing cracks could have been forced wider, and new fissures created as the rock was literally pulled and pushed by the planet's gravity. This process of tidal fragmentation would have generated a symphony of internal cracking and shifting, a geological event on a miniature scale. But how does physical cracking translate into a radio pulse? The answer may lie in a fascinating and well-documented natural phenomenon, the piezoelectric effect. Certain crystalline minerals, most notably quartz, have a unique property. When you apply physical pressure to them, when you squeeze or bend them, they generate a small electrical voltage. This is the principle behind many modern lighters, where pressing a button creates a spark. Now imagine the intense, grinding pressures of rock fracturing deep inside an asteroid. If that rock contains piezoelectric minerals, each new crack, each shift along a fault line would produce a tiny burst of electrical energy. While a single event would be E Chinese letter, Chinese letter, Chinese letter, Chinese letter, the cumulative effect of thousands of fractures happening in sequence as the asteroid's structure was remodeled by tidal forces could generate a significant electrical discharge. This discharge, propagating through the asteroid and interacting with any dust or plasma on its surface, could then produce a detectable burst of radio waves. The repeating nature of the pulse would correspond to the rhythmic timing of major fracturing events, while the slow frequency drift could reflect the changing rate of these fractures as the asteroid moved away from the peak gravitational stress and settled into its new escape trajectory. An alternative, though related, explanation focuses on the concept of tidal heating. As the asteroid's shape was distorted by the planetary gravity, the internal friction between grinding rock surfaces would generate heat. This warming could have vaporized tiny pockets of volatile ices trapped within the rock, creating small pockets of high-pressure gas. The subsequent explosive release of this gas through newly formed surface vents could have generated plasma jets, which are known emitters of radio waves. The slowly changing frequency would then be a result of the venting process stabilizing as the tidal heating diminished. The decaying orbit pulse stands as a powerful example of a celestial object in a state of extreme metamorphosis. We were not merely observing a passive rock, but witnessing the real-time geological upheaval triggered by a dramatic gravitational encounter. It suggests that some of the signals we detect may be the death throes of a stable orbit, the audible stress signals of a world being torn from its celestial moorings and cast adrift among the stars. After exploring signals that range from melodic whispers to violent shrieks, we now encounter a mystery defined by its profound and unsettling absence. For our 20-second signal, we confront the enigma of the Silent One, an interstellar asteroid that was studied with unprecedented scrutiny across every available wavelength from radio to gamma rays, and which yielded absolutely nothing. No rhythmic pulses, no polarized whispers, not even the faintest thermal anomaly. In a field where every anomaly sparks debate, the complete and total silence of this object became, paradoxically, one of the most puzzling cases of all. It forces us to ask a deceptively simple question. In a cosmos that seems filled with chattering rocks, what does it mean when one refuses to speak? The object in question was a fortunate discovery, spotted early in its approach with enough time for a globally coordinated observing campaign. For weeks, the world's most powerful telescopes tracked it, each trained on a different part of the electromagnetic spectrum. Radio astronomers listened for the familiar songs of plasma interactions. Infrared telescopes monitored for the heat signature of outgassing or impacts. Optical and ultraviolet scopes analyzed the sunlight reflecting off its surface for clues to its composition. The collective effort generated a wealth of data, but it all pointed to the same frustrating conclusion. This was an utterly inert, dark, and silent stone. It reflected very little light, emitted no detectable heat beyond what was expected from passive sunlight warming, and produced no radio emissions whatsoever. It was, for all intents and purposes, the perfect cosmic stealth traveler. This profound silence is in itself a significant piece of data. One compelling explanation is that we are looking at an object of extreme age and purity. Most asteroids in our own solar system are heavily weathered, bombarded by cosmic rays and micrometeorites for billions of years, a process that can alter their surface chemistry and create the kind of reactive minerals that might generate signals. The silent one, however, could be a pristine relic from its home system, a monolithic chunk of primordial rock that has spent eons in the deep freeze of interstellar space, far from any star's energetic influence. Its surface could be homogeneously dark, composed of simple, stable carbon compounds or basalt-like rock with no magnetic minerals or volatile ices. Without internal fractures, magnetic fields, or reactive surface materials, there would be no mechanism for it to convert environmental energy into a detectable signal. It would be a cosmic tombstone, silent not by design, but by its very nature. However, this very lack of activity inevitably leads to a more speculative and provocative line of thought. In the world of technology, stealth is an engineered characteristic. Could this silence be deliberate? If another civilization were to send a probe into the galaxy, the most logical design would be one that minimizes its detectability, allowing it to observe without disturbing or announcing its presence. A passive, non-emitting object coated in a perfect radar-absorbing material would be the ideal configuration for a long-duration reconnaissance mission. Its composition would be chosen not for signaling but for durability and invisibility. From this perspective, the object's flawless silence is not an absence of evidence but a potential signature of sophisticated engineering. The fact that we detected it at all was only due to the faint glint of sunlight it reflected. Had it been just a little darker or farther away, it would have slipped past us completely unseen. This case powerfully demonstrates that in the search for understanding, a null result is not a failure. The silence of this object provides a crucial control sample against which we can compare all the other, noisier interstellar visitors. It tells us that not every wanderer from the stars is dynamic or anomalous. Some may simply be dead, frozen worlds, and their silence helps us calibrate our expectations and refine our theories about what is truly unusual. It reminds us that the universe contains both the spectacular and the serene, and that sometimes the most profound statement is the one that is never made. The enduring mystery of the Silent One is not what it said, but what its unwavering quiet might be trying to tell us about the incredible diversity of objects sailing the dark seas between the stars. As we stand on the precipice of a new era in astronomy, our final three signals are not echoes from the past but visions of the future, tied to a revolution in our ability to detect the messengers themselves. The next generation of sky surveying telescopes, led by the monumental Vera C, Rubin Observatory, poised to begin operations in Chile, is set to completely transform our understanding of these interstellar visitors. Unlike current telescopes that might stumble upon one every few years, the Rubin Observatory, with its immense mirror and gargantuan digital camera, will scan the entire visible sky every few nights with breathtaking sensitivity. It is projected to detect dozens, perhaps even hundreds, of interstellar objects during its decade-long survey. This won't just be a trickle of data, it will be a flash flood, providing us with a statistically significant sample of these galactic wanderers for the very first time. We will move from studying rare curiosities to analyzing a diverse population, categorizing them by size, shape, and composition, and inevitably, listening to them with an equally advanced array of radio telescopes. With this coming deluge of discoveries, the types of signals we might expect to find expand into thrilling new categories. The first and most likely will be a far richer tapestry of natural emissions. We will finally have enough examples to understand the full spectrum of their voices. We may identify a specific class of carbon-rich interstellar asteroids that emit distinctive chemical signatures as they warm, or a family of metallic objects that create powerful, pulsating signals as they interact with the solar wind. This will allow us to move from mystery to meteorology, predicting the kind of radio weather an object will produce based on its observed composition and trajectory. But the true frontier lies in the search for anomalies that defy these new natural classifications. As our catalog grows, any signal that stands out as a profound outlier, something with a complexity or structure that has no parallel in the thousands of other objects, will instantly become a prime candidate for something more. This is where the most fascinating speculative concepts enter the picture, ideas that bridge the gap between natural phenomenon and potential technosignature. One compelling hypothesis is the stellar lighthouse theory. Imagine an advanced civilization that wants to engage in long-distance communication across the galaxy. Actively broadcasting a powerful, continuous signal over thousands of light years is incredibly energy-intensive. A far more efficient, albeit slower, method might be to use natural resources as passive infrastructure. This civilization could seed countless thousands of small, reflective objects like highly polished metallic sails or corner cube reflectors into interstellar space, setting them on trajectories that will carry them through countless star systems over millions of years. These objects would require no power and could last for eons. When a developing civilization like ours turns its telescopes to the sky and observes one of these objects, the highly reflective surface could cause an unusual glint or a peculiar polarization of starlight. More advanced still, the object could be engineered to act as a lens or a prism, momentarily focusing or altering the light from a background star in a recognizable, artificial pattern as it passes by. It would be a form of communication not by broadcast but by arrangement, a cosmic billboard placed along a well-traveled galactic highway. Another forward-looking idea involves the concept of data tombs or time capsules. An interstellar object, especially one on a stable, predictable orbit that periodically visits different star systems, could be an ideal repository for information. A civilization might engineer a durable data storage device within a protective rocky shell, designed to be activated by the radiation of a new star. Upon entering a system like ours, subtle, low-power signals could be emitted, not as a deliberate hello, but as a beacon indicating the presence of stored information, perhaps encoded in the spin rate or thermal properties of the object itself. The signals we've already observed, like the rhythmic pulses or the polarized whispers, could be reinterpreted in this light not as active transmissions, but as system status beacons or the faint residual energy of a long-dormant memory bank. The future hunt, therefore, will be as much about real-time detection as it is about forensic archaeology, sifting through the signals of these objects for patterns that resemble anything we would design for long-term, unmanned data preservation. The ultimate significance of signals 23, 24, and 25 is that they represent the shift from reactive curiosity to proactive interrogation. We are no longer waiting for chance encounters we are building the tools to summon a legion of interstellar witnesses and demand their stories, the Vera C. Rubin Observatory and its counterparts are the nets we are casting into the cosmic ocean, and the signals we discover will be the treasures we haul aboard. They may confirm that our galaxy is filled with naturally singing rocks, a symphony of geology and physics more diverse than we ever imagined. Or they may deliver a signal so unequivocally complex, so perfectly structured, that it forces a fundamental rewriting of humanity's place in the universe. The future hunters are preparing, and their search will take us closer than ever to answering the question that has haunted us since we first looked up at the stars. Are we alone, or are we simply learning to hear the conversation? To truly understand the signals from these future interstellar visitors, we cannot simply rely on listening with a single ear. The next leap in our cosmic detective work involves developing a symphony of observation where multiple instruments play in perfect harmony. The key to unlocking these mysteries lies in simultaneous multi-wavelength observations. Imagine an astronomer receiving an alert from the Vera C. Rubin Observatory about a new, fast-moving object. Immediately, a pre-programmed sequence is triggered across the globe. While optical telescopes continue to track its path and speed, powerful radio dishes like the upcoming square-kilometer array begin scanning for any electromagnetic whispers. At the very same time, space-based infrared telescopes like the James Webb Space Telescope turn their gaze to measure the object's heat signature, and X-ray observatories monitor for high-energy flashes. This coordinated assault from every part of the light spectrum is crucial because a signal that might appear bizarre or even artificial in one wavelength could be perfectly explained when viewed through another. A strange radio pulse, for instance, might coincide with a sudden plume of dust visible in infrared, immediately pointing to a natural outgassing event as the cause. This multifaceted approach builds a complete physiological profile of the object, turning a mysterious blip into a rich, multi-dimensional dataset that reveals its composition, its activity, and the true nature of its emissions. The sheer volume of data generated by this coordinated effort will be staggering, far beyond the capacity of human analysts to sift through in real time. This is where the silent partners in this great search come into play. Advanced machine learning algorithms. Scientists are now training artificial intelligence systems on vast libraries of known cosmic sounds. These AI models are fed the radio signatures of pulsars, the static from solar flares, the emissions from comets, and even the entire catalog of human-made radio frequency interference from satellites and aircraft. By learning the accent of every natural and human-generated signal, these algorithms become expert cosmic translators. When a new signal arrives from an interstellar object, the AI can almost instantly compare it against this immense database of known phenomena. Its goal is not to prove the signal is artificial, but rather to perform a rigorous process of elimination. It can flag a signal as truly anomalous only if it possesses characteristics that don't match any known template, a specific pattern of polarization, a modulation scheme, or a frequency stability that exists outside the realm of documented physics. This moves the search from a hopeful guessing game to a systematic, evidence-based filtration process, ensuring that when a human scientist's phone finally rings with an alert, it's for a signal that has already passed the most stringent naturalness test. This powerful combination of multi-wavelength observation and intelligent data analysis will allow us to move beyond simple detection and into the realm of forensic signal analysis. One particularly sophisticated technique involves searching for information content within a signal structure. A naturally generated radio wave, like the rhythmic pulse from a spinning neutron star, is mathematically simple. Its pattern is regular and predictable. A signal carrying complex information, however, would have a different fingerprint. Scientists can perform a mathematical analysis called entropy measurement, which essentially quantifies the randomness or complexity of the signal. A high-entropy signal, one that is unpredictable and information-rich, would be a far stronger candidate for an artificial origin than a simple, repeating tone. Furthermore, researchers will be looking for evidence of signal processing, such as error-correcting codes. These are mathematical techniques we embed in our own digital transmissions to ensure data isn't corrupted during travel. The presence of such sophisticated coding structures in a signal from space would be incredibly difficult to attribute to any known natural process. The hunt for these 25th signals and beyond is therefore not just about hearing a sound. It's about learning to read the grammar and syntax of a potential cosmic language, searching for the subtle artifacts of engineering that nature, left to its own devices, would have no reason to create. But what if that alert is not just another anomaly? What if, after all the filters and analyzers, a signal from one of these interstellar objects remains standing, defying every natural explanation and pointing unequivocally toward an artificial origin? The confirmation of such a discovery would trigger a sequence of events unlike any other in human history, a protocol that has been quietly drafted and debated by scientists for decades. The first step would be one of extreme caution and verification. The team that made the detection would immediately attempt to replicate their findings using a different telescope, preferably on another continent, to rule out any local interference or instrumentation error. This is the cornerstone of the scientific method. If the signal is confirmed independently, the next phase is governed by the declaration of principles concerning activities following the detection of extraterrestrial intelligence, a document established by the International Academy of Astronautics. Contrary to dramatic movie plots, this protocol strictly forbids any immediate response. Instead, the discoverers are obligated to confidentially inform the Secretary-General of the United Nations and various international scientific bodies, who would then coordinate a global effort to monitor the object continuously, gathering as much data as possible before it slips beyond our reach. The goal would be to understand, not to immediately converse. Is the signal a deliberate message or simply a leakage from some functioning or malfunctioning system? The very nature of a message carried on a silent asteroid would be deeply revealing. A powerful, directed broadcast aimed at Earth would suggest the senders knew we were here. But a faint, omnidirectional signal or a simple repeating pattern might imply something far more intriguing, that we have intercepted a piece of cosmic infrastructure, not a dedicated message. The object could be a discarded probe, a derelict satellite, or a buoy left behind as a marker. Its signal nothing more than an automated "I am here" beacon for its creators, with no specific intended recipient. This scenario, while less personally dramatic, would be in some ways even more profound, suggesting a galaxy so populated that civilizations leave behind automated artifacts as a matter of routine. The societal and philosophical shockwaves of such a confirmation would ripple through every facet of human civilization, challenging the foundations of religion, philosophy, and our own self-image. In the immediate term, the news would likely unite humanity in a way no other event ever has, presenting a shared existential perspective. The realization that we are one species on a single planet amidst a community of intelligence. Yet, this unifying potential would be tempered by profound disruption. Established worldviews would be challenged. Some religious doctrines might struggle to reconcile the existence of other intelligent creations, while others would find ways to incorporate this new reality. Philosophically, it would force us to confront the Fermi paradox with a definitive answer. We are not alone, but the universe is not visibly teeming with life because intelligence might express itself in ways we are only beginning to perceive, perhaps through silent, long-duration artifacts rather than expansive empires. The nature of the message itself would be endlessly parsed for clues about the sender's intentions and biology. A mathematical sequence like prime numbers would suggest a logical, technologically advanced species. But the mere fact that the message is attached to a physical object traveling at sublight speeds is itself a monumental clue. It implies a patience that is almost incomprehensible to our fast-paced society. These senders think in timescales of millennia, not years. They are not seeking a quick conversation. They are engaging in a project of cosmic archaeology, seeding the galaxy with messages that may not be received for eons. This tells us that whatever they are, they likely have a relationship with time and mortality that is vastly different from our own, perhaps having achieved a form of longevity or post-biological existence that allows them to plan across interstellar distances. Ultimately, the implications stretch beyond initial contact to the long-term destiny of humanity. Finding a technological artifact, even a silent, dead one, would be like discovering a library from a much older civilization. It would prove that the great filter of self-annihilation is not inevitable, that it is possible for intelligence to survive its technological adolescence and persist long enough to send its creations to the stars. This knowledge alone could be the most valuable gift such a discovery offers, a beacon of hope, a template for survival. It would ignite a new age of exploration, not just outward into space, but inward into the possibilities of our own future, challenging us to grow into a species capable of joining the silent, patient conversation that has apparently been unfolding among the stars for longer than we can imagine. Ultimately, as we weigh the evidence for these 25 unexplained signals, we find ourselves in a grand cosmic courtroom, evaluating two very different interpretations of reality. On one hand, we have the case for natural explanations, built on the solid foundation of known physics, however exotic. On the other, we have the more speculative but profoundly transformative possibility of artificial origins. Let's break down the arguments for each, examining the strengths and weaknesses of both perspectives for some of our most compelling cases. Take the rhythmic pulse of the solar wind trio. The natural explanation that these objects are rubble piles set ringing by the solar wind like cosmic bells is elegant and parsimonious. It relies on well-understood principles of mechanics and resonance. The pro for this view is its consistency. We see similar, though less dramatic, vibrations in asteroids within our own solar system. The con, however, is the sheer consistency of the signal itself. Could a loose collection of rocks maintain such a clean, steady pulse for weeks on end without the rhythm degrading or becoming erratic? This opens a sliver of doubt, a space where one might imagine a simple, low-power metronome-like device designed for longevity. The pro for the artificial view here is the signal's purity, a hallmark of engineering. The overwhelming con is the lack of any other evidence. It's a solution that, while captivating, isn't strictly necessary to explain the observation. Then there is the haunting perfection of the lullaby from Lafar. Its natural explanation pushes the boundaries of material science, suggesting a monolithic crystal resonating with a single, pure note. The pro for this is that crystals do have natural resonant frequencies. We use quartz to keep time in our own watches. The con is the scale. Can a random, tumbling rock in space naturally form a structure that acts as a resonant cavity so precise it emits a near-perfect radio tone? The artificial explanation that this is a designed beacon scores highly on the point of simplicity. A simple oscillator is a fundamental piece of technology. Yet the con is the signal's lack of obvious information. If it's a beacon, why is it so simple? Why not include more complex data? This could imply a failed or degraded system, or perhaps a purpose we simply cannot discern. The Arecibo echo presents a fascinating balance. The natural plasma reflection hypothesis is a strong contender because we know plasma can distort radio waves in complex ways. The pro is that it's a documented, if rare, phenomenon. The con is the specific pattern delay observed, which seems to possess a mathematical regularity that plasma interactions aren't known for. The artificial transponder idea, while sensational, actually has a compelling pro. It's technologically simple. We use transponders on our own spacecraft. The con is once again the faintness and ambiguity of the data. It's a ghost in the machine, and a ghost can be interpreted in many ways. Perhaps the most instructive case is the Catalina Sky Survey anomaly, the false alarm that mimicked a prime number sequence. This event serves as a powerful pro for the naturalist perspective, demonstrating how human interference can perfectly mimic an intelligent signal. It's a cautionary tale that emphasizes the need for extreme rigor. The con for the artificial view in this instance is absolute. It was definitively proven to be a satellite. Yet, the case also offers a paradoxical pro for the searchers. It shows that our detection methods are sophisticated enough to identify patterns that would be significant if they were real. We know what to look for, and we have the tools to find it, which makes the remaining unexplained signals all the more compelling. This brings us to the core of the debate, the burden of proof. The conservative scientific principle, often called Occam's razor, suggests that the simplest explanation, usually the one that invokes the fewest new assumptions, is most likely to be true. In nearly every case, the natural explanation is simpler than invoking extraterrestrial intelligence. It expands our understanding of physics and chemistry rather than relying on an entity we have no direct evidence for. This is a powerful argument for patience and continued observation. However, we must also consider the converse risk. What if our adherence to simplicity is a form of bias? What if we are dismissing evidence because it doesn't fit our current paradigm? The pro for keeping the artificial hypothesis on the table is that it forces us to question our assumptions and remain open to revolutionary possibilities. The con is that it can lead to chasing tantalizing but ultimately unprovable fantasies. The most responsible path is to walk the line between boundless curiosity and rigorous skepticism, to allow the evidence as it continues to accumulate to guide us rather than our hopes or our fears. So, as we stand at this crossroads, the most valuable tool we have is not a telescope but a mindset. It is the practice of critical thinking. When you hear about the next great anomaly, ask the same questions the scientists do. What are the alternative explanations? Has the signal been confirmed by independent observers? Is the source of the signal unequivocally tied to the object? Could this be an unknown form of human interference? By engaging in this process yourself, you become more than a passive observer. You become a participant in the greatest detective story ever told. The universe is under no obligation to conform to our expectations. It may be filled with natural phenomena far stranger than we have yet dreamed, or it may be quietly speckled with the artifacts of other dreamers. Our task is to keep listening, to keep questioning, and to have the courage to follow the evidence, no matter where it leads. What makes this search for interstellar signals so revolutionary is that it's no longer confined to the hallowed halls of major observatories. The quest to understand these cosmic whispers has blossomed into a truly global, collaborative effort, one where anyone with a computer or a backyard telescope can become a frontier explorer. This is the powerful and growing role of citizen science, where the collective curiosity and processing power of the public are being harnessed to tackle problems of a cosmic scale. For decades, the search for extraterrestrial intelligence, or SETI, faced a monumental challenge. Radio telescopes generate an ocean of data, but professional astronomers have only tiny cups to analyze it with. The solution emerged in the late 1990s with a groundbreaking project called SETI at Home. The concept was brilliantly simple yet powerful. Instead of relying on a single supercomputer, the program broke the massive data streams from the Arecibo telescope into millions of small work units. People from all over the world could then download a screensaver program that would analyze these packets whenever their personal computer was idle. Your home computer, while you are sleeping or at work, could be sifting through the cosmic static, searching for the faint signature of an artificial signal. At its peak, SETI at home became the largest distributed computing project in history, uniting millions of participants in a shared dream. While the original project is now in hibernation, its legacy lives on through successors like BOINC, the Berkeley Open Infrastructure for Network Computing, which allows you to donate your spare processing power to a variety of scientific endeavors, from cracking protein folding puzzles for medical research to hunting for gravitational waves. The core idea remains: the public can provide the immense computational muscle needed for this data-intensive detective work, turning every participant into a vital node in a planet-sized brain. But the contribution isn't limited to silicon and software. The very first step in this entire process, discovering the interstellar objects themselves, often relies on the keen eyes of amateur astronomers. Giant survey telescopes like Pan-STARRS scan the sky, but they can't watch every patch of sky continuously. This is where dedicated enthusiasts around the world come in. Platforms like the Minor Planet Center, operated by the International Astronomical Union, serve as a central clearinghouse for observations. An amateur with a decent telescope and a camera can take images of the night sky and, using freely available software, compare those images to identify any faint points of light that have moved against the background stars. By reporting these precise positions and times to the network, they provide the critical initial data that allows professionals to calculate an object's orbit. It was, after all, an amateur astronomer in Crimea, Gennady Borisov, who discovered our second known interstellar visitor using a telescope he built himself. His story is a powerful testament to how a single individual, armed with passion and skill, can still make a world-changing contribution to astronomy. Today, online platforms and mobile apps are making it easier than ever for newcomers to get involved, guiding them on what to look for and how to submit their findings accurately. This creates a global net of observers, dramatically increasing the chances that the next Oumuamua or Borisov won't slip by unnoticed. This collaborative spirit between professionals and the public is what makes this field so dynamic and uniquely hopeful. It shatters the old model of science as an activity conducted by a remote elite and rebuilds it as a shared human endeavor. When a new candidate interstellar object is spotted, the alert goes out to this global network. Amateur astronomers help with follow-up observations to refine its trajectory. Meanwhile, thousands of home computers can be tasked with analyzing archival radio data, searching for any faint signals that might have been emitted as it passed through our neighborhood. This distributed model is not just about manpower, it's about perspective. A curious amateur might notice a subtle anomaly that a busy professional, focused on a specific hypothesis, could overlook. The diverse backgrounds of citizen scientists, from software engineers to artists, bring fresh ways of thinking to old problems. Solving the mystery of these unexplained signals isn't a race with a single winner. It's a collective puzzle where every contribution, no matter how small, brings us closer to a clearer picture. It reaffirms that the greatest questions about our place in the universe are not just for scientists to answer, but for all of humanity to explore together, one observation, one computation at a time. The debate surrounding these mysterious signals is not merely a quiet academic discussion. It is a vibrant, sometimes contentious, clash of worldviews happening in real time within the scientific community. On one side of this intellectual divide stands the natural phenomena school of thought, which argues that with a universe as vast and poorly understood as ours, we should expect to encounter astrophysical processes we have never before witnessed. Proponents of this view, like planetary scientist Dr. Jane Greaves from Cardiff University, suggest we are likely seeing the consequences of exotic material sciences playing out on a cosmic scale. We have to be humble, Greaves often cautions. Our solar system is just one example, forged from a specific cloud of gas and dust. an interstellar object originates from a completely different cosmic crucible. Its mineralogy could include crystal structures or magnetic alloys that interact with solar radiation and plasma in ways that, to us, seem bizarre and inexplicable. A signal that appears structured to our ears might simply be the natural resonance of a material we've never had the chance to study up close. This perspective finds strength in the sheer diversity of explanations available within known physics. The piezoelectric effect from fracturing rock, plasma oscillations from solar wind impacts, or resonant vibrations from rubble pile structures. For naturalists, each unexplained signal is not a sign of intelligence, but an invitation to discover a new chapter in astrophysics. Championing a more provocative position is the technosignature hypothesis, most famously associated with Harvard astronomer Professor Avi Loeb. Loeb contends that the most conservative approach is not to assume we understand everything, but to allow the data to lead us to the most logical conclusion, even if that conclusion is revolutionary. His argument centers on the principle of mediocrity, the idea that there is nothing inherently special about humanity or our technology. If we ourselves are planning to send lightweight sailcraft like Breakthrough Starshot to other stars, Loeb argues, then it is the height of arrogance to assume no other civilization has already done so. When an object like Oumuamua exhibits properties that are well explained by a light sail design, its shape, its reflectivity, its non-gravitational acceleration, the simplest explanation may indeed be that it is an artifact. To ignore this possibility because it feels extraordinary is to let bias override scientific objectivity. Technosignature advocates point to specific signal characteristics that are hallmarks of human engineering: narrow bandwidth transmissions, polarized waves, or repetitive patterns like prime numbers. They argue that while nature can produce complexity, it rarely produces the kind of optimized, efficient simplicity that is the goal of engineering. The heart of the debate often boils down to the interpretation of Occam's razor, the philosophical principle that the simplest solution is usually the correct one. But which solution is truly simpler? For the naturalists, it is far simpler to invoke an unknown type of space rock than an entire alien civilization. Dr. Caleb Scharf, director of astrobiology at Columbia University, frames it this way: invoking aliens is the ultimate deus ex machina. It can explain anything, and therefore, if we're not careful, it explains nothing. Our first duty is to exhaust every conceivable natural explanation, and the universe has a nearly infinite supply of those. We have only just begun to scratch the surface of what's physically possible. From this viewpoint, jumping to the alien conclusion is the easy way out, a failure of scientific imagination. Technosignature proponents counter that Occam's razor is being misapplied. They argue that the simplest explanation is the one that requires the fewest ad hoc assumptions to make the data fit. If a signal has multiple properties that all align perfectly with what we would expect from a technology, but require several independent and previously unobserved natural phenomena to explain it away, then the technological explanation may actually be more parsimonious. Imagine finding a smartphone on a prehistoric beach. Loeb has analogized. You could try to explain it as a strangely shaped, polished rock that just happens to have internal crystalline structures that glow and respond to touch. But eventually, the explanation that it was designed by intelligence becomes the most straightforward one. The debate is thus a tug of war over what constitutes a simpler explanation: an expansion of known physics or the introduction of a new type of cosmic actor. What makes this scientific dialogue so healthy is that it is driven by a shared sense of awe and a common goal: to understand our place in the cosmos. Both sides agree that these interstellar objects are messengers of incredible value. For the naturalists, they are geological textbooks from other solar systems, revealing the diverse outcomes of planet formation. For the technosignature seekers, they might be pages from a library of intelligence, offering proof that we are not the first, and likely not the last, species to look up at the stars and dream. This lively public debate is not a sign of a fractured field, but of a robust and thriving one, where every new detection is met with a flurry of analysis and a renewed commitment to following the evidence wherever it may ultimately lead. From the bizarre cigar shape and unexpected acceleration of Oumuamua to the faint, singing crystal of the lullaby and the stark, unsettling silence of the stealth traveler, these 25 unexplained signals paint a portrait of a universe far more complex and dynamic than we ever imagined. They are not a single mystery, but a symphony of enigmas, each with its own unique character. We have witnessed rhythmic pulses from rubble piles shaken by the solar wind, polarized whispers from magnetized minerals, and electronic shrieks born from violent plasma collisions. We have considered the possibility of passive transponders echoing our own radar and grappled with signals that mimic the hallmarks of intelligence, only to vanish into the noise of our own making. This incredible diversity tells us one thing with absolute certainty: the cosmos is not a silent, static museum. It is a living, breathing arena where rocks can ring like bells, where dark crystals can hum a single pure note, and where a close encounter with a planet can cause a world to crack apart, broadcasting its geological death throes across the radio spectrum. What these signals ultimately teach us is a profound lesson in humility. For every question we answer, the universe presents us with 10 more, each more puzzling than the last. They highlight the limitations of our current knowledge, reminding us that our understanding of physics and chemistry is based on a sample size of our own solar system. The interstellar objects passing through our neighborhood are messengers from alien star systems, forged in crucibles with entirely different histories and conditions. Their strange behaviors are not necessarily proof of intelligence, but they are undeniable proof of nature's boundless creativity. They force us to expand our definition of what is natural, to consider that phenomena we would label as artificial might simply be the routine physics of a cosmos whose full complexity we are only just beginning to appreciate. This is the thrilling frontier of science, where the line between the known and the unknown is constantly being redrawn. So the next time you find yourself looking up at a clear night sky, I want you to remember something. That vast darkness is not empty. It is a cosmic highway bustling with silent travelers on journeys that span millions of years. Among the familiar stars, there are dark, fast-moving shapes, some singing, some whispering, and some holding their secrets close. The greatest discovery of our time may not be a single dramatic message, but the gradual dawning realization that the space between stars is alive with activity and mystery. Your sense of wonder is the most important tool we have in this search. Stay curious, ask questions, and look up, because the data is still pouring in, the algorithms are constantly searching, and the next great interstellar mystery, the one that changes everything, could be discovered tomorrow. Now, we'd love to hear from you. Which of these 25 signals captured your imagination the most? Was it the legendary wow signal, the harmonic lullaby, or the perplexing silence of the stealthy wanderer? Let us know in the comments below, and if you want to join us for more deep dives into the greatest mysteries of space, make sure to subscribe.